Tomorrow, October 29th, 2025, at 11:47 Universal Time, 3i Atlas will brush past the Sun at its closest point, Perihelion, moving faster than any object of its kind we've ever recorded. But right now, as you listen, 3i Atlas has achieved something far more unsettling than speed. For 12 days, centered perfectly on Perihelion, the object has vanished. Not faded, not escaped, but disappeared behind the unwavering shield of the Sun. This is the 12-day plan, an operational blackout so precise, so absolute, that not a single telescope on Earth or in orbit can witness what happens next. It isn't an accident. In these 12 days, between October 24th and November 4th, 3i Atlas reaches its peak. Maximum energy, maximum velocity, and maximum potential for change, while hidden in a span of engineered invisibility. Every move, every transformation, every possible burn or maneuver, protected, impossible to detect. Solar conjunction, astronomers might call it, a routine blind spot. But for this object, routine isn't the story. Timing is. You're told it's coincidence, a trick of orbits, a regular rhythm of planetary motion. But what lingers is the possibility of plan, that these 12 days aren't just blackout, but appointment. The perfect cover, the perfect moment, the perfect opportunity to do whatever must never be seen. What happens now in the absolute heart of the crossing is lost to us. This is the hidden axis around which the entire journey turns, the 12-day plan executed in darkness. Because at Perihelion, the physics itself changes. This is where any comet becomes most active, most volatile, where surges of heat erupt buried ices, and where even natural forces can rewrite a trajectory. But for anything with intention, Perihelion is more. It's the single point where a maneuver, an engine burn, a shift in direction, delivers maximum effect for minimum effort. The Oberth effect, it's called, and every spacecraft engineer on Earth knows this principle. At the lowest point in a gravity well, a burst of energy is magnified. A braking burn here isn't just efficient, it's decisive. If you wanted to change your fate in this solar system, you would wait for this exact window. The 12 days when you are hidden from every eye, every instrument, every analysis. The Sun as both shield and accomplice. No evidence, no data, just the perfect moment for transformation. And that is what 3i Atlas has, in this engineered interval of darkness, in a plan that may not be a myth, but a method forged by the stars themselves. But there is more. The blackout is not merely about hiding from Earth-based telescopes. It is about hiding from all observation platforms in the inner solar system. During conjunction, the Sun floods the electromagnetic spectrum with noise. Radio telescopes cannot penetrate the coronal plasma. Infrared observatories are blinded by thermal radiation. Ultraviolet instruments see only the chromosphere. Even spacecraft positioned at Mars, which observed 3i Atlas during its close approach on October 3rd, more than 2 weeks before conjunction, lose line of sight as the object moves behind the Sun relative to their position as well. As of October 21st, 3i Atlas has entered a communications dead zone. Not just for us, but for any observer anywhere in the inner solar system. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter captured images of the Comet during its earlier Mars flyby. But with Perihelion upon us, those spacecraft are now on the wrong side of their orbits, their view obstructed by solar glare, by trajectory, by geometry itself. NASA's Curiosity and Perseverance rovers on the Martian surface lack the capability to observe objects in space. Even the GOES 19 weather satellite circling in geostationary orbit might theoretically catch a glimpse near Perihelion, but that remains speculative and so far unconfirmed. For all practical purposes, 3i Atlas is now truly alone with the Sun. The plan, if it is a plan, accounts for this. You're observing an object that discovered on July 1st, 2025, moving inbound at 58 kilometers per second, faster than any previous interstellar visitor. It follows a trajectory inclined just 5 degrees from the ecliptic plane, a retrograde path that brings it unusually close to multiple planets in sequence. On October 3rd, it passes within 0.19 astronomical units of Mars. On November 3rd, it will pass within 0.65 astronomical units of Venus. On March 16th, 2026, it will pass within 0.36 astronomical units of Jupiter. These are not glancing encounters. These are geometrically improbable alignments. A statistical analysis conducted by independent researchers calculated the probability of an interstellar object arriving from a random direction in the galaxy, achieving such close approaches to 3 major planets in sequence. The result? Approximately 0.005%, 1 in 20,000. You can argue this is coincidence, but coincidence is not explanation. Coincidence is the word we use when we encounter a pattern we cannot or will not attribute to intent. And here is where the geometry becomes more than uncomfortable. It becomes predictive. If 3i Atlas was simply falling through the solar system on a natural unguided trajectory, the timing of its perihelion would be random with respect to Earth's position in its orbit. There is no physical reason why an interstellar comet, ejected from a distant star system billions of years ago, should arrive at perihelion on a date that places Earth on the opposite side of the Sun. The probability of this alignment occurring by chance, that perihelion coincides with solar conjunction as seen from Earth, is roughly 7%. 7% is not impossible, but it is worth noting. 7% means that 93% of the time, this would not happen. 7% means that if you were to plot 1,000 interstellar trajectories at random, only 70 would naturally achieve this configuration. And yet, here we are. The 12-day plan, as we will call it, begins not on the day of perihelion, but on the day the object enters the forbidden zone. October 6th is when 3i Atlas becomes unobservable from Earth. October 29th is when it reaches perihelion. The intervening 23 days are preparation. The 8 days after conjunction, leading into perihelion, are execution. The subsequent weeks, as the object remains hidden while departing the inner solar system, are confirmation and concealment of the outcome. During this time, several events could occur without detection. A braking burn, a sustained thrust maneuver designed to reduce velocity and circularize the orbit, would be invisible. The thermal signature would be lost in the solar glare. The propellant exhaust would be indistinguishable from the natural cometary outgassing already observed. If 3i Atlas is not a comet but a spacecraft, or if it contains propulsion systems embedded within a cometary shell, this is the moment to activate them. The Oberth effect guarantees maximum efficiency. The solar conjunction guarantees zero oversight. An energy collection event, deploying solar panels, unfurling light sails, or activating radioisotope systems to harvest energy from proximity to the Sun, would similarly go unnoticed. The object will be bathed in 33 gigawatts of solar radiation at perihelion. For a natural comet, this energy drives sublimation. For a designed system, this energy could be stored, converted, utilized. We would see none of it. A probe deployment, releasing secondary payloads, sub-satellites, or daughter craft on divergent trajectories, would occur in perfect stealth. Any object released near perihelion inherits the parent body's velocity and benefits from the same Oberth boost. A small probe separating with even a modest delta V could be redirected toward Mars, Venus, or Earth, arriving months later on a trajectory that appears independent of the parent. By the time we detect the secondary object, 3i Atlas will be millions of kilometers away, its role as launch platform undetectable. These are not fantasies. These are mission profiles. These are the maneuvers that human spacecraft would execute if we possessed the capability to send an interstellar probe and the strategic requirement to conceal its actions. The question is not whether such maneuvers are possible. The question is whether we are willing to consider that an interstellar object might employ them. The institutional response has been silenced by misdirection. When asked about the conjunction blackout, space agencies emphasize that it is a natural phenomenon. This is true but incomplete. When asked about the orbital alignment, astronomers cite the statistics of interstellar object detection. This is accurate but evasive. When asked about the chemical anomalies and the trajectory coincidences, the response is to frame these as separate curiosities, unrelated data points that happen to cluster around the same object. But they are not unrelated. They are components of a pattern, and the pattern resolves into a plan. The 12-day plan does not require 3i Atlas to be artificial in origin. It requires only that we acknowledge what the data allows, that an object arriving with these characteristics, at this time, with this trajectory, achieves a window of total invisibility during the moment when any strategic action would be most advantageous. Whether by chance or by design, the result is the same. We are blind when we most need to see. On November 14th, 3i Atlas will emerge from behind the Sun, observatories will reacquire it, spectroscopy will resume, astrometry will measure its position, and we will be told that nothing unusual occurred, that the object followed its predicted path, that no anomalies were detected, that all is as expected. But how would we know? What could we have seen? If a maneuver occurred at perihelion, executed during the 8 days of invisibility between conjunction and closest approach, the change in trajectory would be small enough to attribute to outgassing forces or measurement uncertainty. If energy was harvested, we would see only a comet that brightened and then faded, consistent with thermal models. If probes were deployed, we would not see them until they revealed themselves, if they revealed themselves at all. The plan does not require us to detect it. The plan requires only that we remain unaware that it was executed. This is the nature of concealment at astronomical scale. You do not hide the object, you hide the moment. You do not evade the observer. You position yourself such that observation becomes physically impossible. The Sun is the largest occulting disk in the inner solar system. 3i Atlas has used it perfectly. We will return to the question of intent. We will examine the premeditated path, the unnatural chemistry, the improbable age. But first, you must understand what makes the 12-day plan so elegant. It is not the complexity of the deception, it is the simplicity. The plan requires no faster-than-light travel, no exotic physics, no violation of known science. It requires only an understanding of orbital mechanics, an appreciation for timing, and a trajectory designed, or fortunate enough, to place the object behind the Sun at the exact moment when action is required and observation is impossible. On October 29, 2025, something will happen at perihelion. We will not see it. We cannot see it. The geometry forbids it. The physics demands it. And when 3i Atlas reappears, we will be left with data that fits the model of a comet, because that is the only model we are permitted to test. But absence of evidence is not evidence of absence, and the absence of observation is not the absence of event. The 12-day plan is not a hypothesis. It is a description of opportunity. Whether that opportunity was exploited is a question we may never answer. But the opportunity existed, and it existed with a precision that defies comfortable explanation. The trajectory of 3i Atlas is not random. This is the first conclusion we must accept if we are to understand what makes this object different from every natural comet ever observed within our solar system. When an object arrives from interstellar space, it can approach from any direction in three-dimensional galactic space. It can enter at any angle relative to the plane of the solar system. It can pass by at any distance from the Sun, from barely grazing the heliopause to plunging deep into the inner system. The combinations are effectively infinite. And yet, 3i Atlas arrives on a path that achieves three things simultaneously: near perfect alignment with the ecliptic plane, sequential close approaches to three major planets, and perihelion during solar conjunction. The probability of this combination occurring by chance is not zero, but it is small enough to warrant the question we opened with: is this trajectory found, or is it chosen? Let us begin with the numbers that define the path. On July 1st, 2025, when the Atlas Survey Telescope in Rio Hurtado, Chile, first detected the object, preliminary orbital calculations immediately revealed its interstellar nature. The eccentricity was measured at 6.4, far beyond the threshold of 1. 0 that separates bound orbits from unbound ones. For context, an eccentricity of exactly 1.0 describes a parabolic trajectory, the boundary case where an object has just enough velocity to escape the Sun's gravity but no more. Anything above 1.0 is hyperbolic, meaning the object is moving too fast to ever be captured. The higher the eccentricity, the straighter the trajectory appears, and the faster the object is moving relative to the Sun. An eccentricity of 6.14 is extreme. It means that 3I Atlas is traveling at 58 kilometers per second relative to the Sun when far from its gravitational influence, a velocity termed the hyperbolic excess velocity. This is more than twice the speed of 1I, the first confirmed interstellar visitor, which had a hyperbolic excess velocity of 26 kilometers per second. It is nearly twice the speed of 2I Borisov, the second interstellar object, which traveled at 32 kilometers per second. 3I Atlas is the fastest interstellar object ever detected. It is also the most hyperbolic, with an eccentricity that dwarfs 1.2 and Borisov's 3.4. Speed alone does not imply intent, but speed combined with trajectory does. The path of 3I Atlas is inclined at 175 degrees relative to the ecliptic plane, the plane in which Earth and the other planets orbit the Sun. An inclination of 175 degrees is equivalent to 5 degrees in the opposite direction, meaning the object is traveling in a retrograde orbit, moving counter to the direction in which the planets revolve, but doing so at an angle of only 5 degrees from the ecliptic. This is the most closely aligned interstellar trajectory ever observed. Oumuamua approached at an inclination of roughly 23 degrees from the ecliptic. Borisov came in at approximately 44 degrees. Both trajectories were significantly tilted relative to the plane of planetary orbits. 3I Atlas is nearly coplanar. This matters because the ecliptic is not a random reference frame. It is the plane of the solar system's formation, the disk of debris from which the planets coalesced 4.6 billion years ago. Objects native to the solar system, asteroids, comets, Kuiper belt objects, naturally orbit within or near this plane because they originated from it. Interstellar objects, by contrast, arrive from random directions in the galaxy. There is no reason for an interstellar comet ejected from a distant star system and drifting through the Milky Way for billions of years to arrive aligned with our ecliptic. The probability is not high. Yet here it is. The alignment has consequences. A trajectory inclined at only 5 degrees from the ecliptic passes through the gravitational neighborhoods of multiple planets. This is geometry, not conjecture. When you enter the solar system nearly parallel to the plane in which all the major bodies orbit, you increase the likelihood of close encounters. But likelihood is not certainty. The timing must also align. The planets must be in the correct positions along their orbits at the moment 3I Atlas passes through, and they are. On October 3, 2025, 3I Atlas passed within 2.19 astronomical units of Mars. 1 astronomical unit, defined as the average distance between Earth and the Sun, is approximately 150 million kilometers. At 0.19 AU, the object came within 28.4 million kilometers of Mars. This is not a grazing encounter, this is a close approach, near enough that Mars-based spacecraft were able to observe the comet in detail. The European Space Agency's ExoMars Trace Gas Orbiter captured images of the object using its color and stereo surface imaging system. ESA's Mars Express attempted observations, though exposure times proved insufficient to resolve the faint target. NASA's Mars Reconnaissance Orbiter also tracked the comet, though data was not released due to institutional delays we will address later. On November 3, 2025, less than 1 week after Perihelion, 3I Atlas will pass within 0.65 AU of Venus, approximately 97 million kilometers. This is still a significant separation, but it places the object within Venus's gravitational sphere of influence. Any spacecraft in Venus orbit could observe the comet. Any instruments positioned on the planet's surface, if such instruments existed, would have an unobstructed view. On March 16, 2026, more than 4 months after Perihelion, 3I Atlas will pass within 0.36 AU of Jupiter, roughly 54 million kilometers. This is closer than the Mars encounter in absolute distance, but because Jupiter's hill sphere, the region in which its gravity dominates, extends much farther than Mars's, the flyby is less dynamically significant. Nevertheless, NASA's Juno spacecraft, currently in orbit around Jupiter, may be able to observe the comet, though mission planners have stated that fuel limitations and engine issues make redirection unlikely. 3 planets, 3 close approaches, sequential, separated by weeks, not years. Let us calculate the probability. The researchers who first analyzed the 3I Atlas trajectory ran a statistical simulation. They assumed that an interstellar object arriving from a random direction in the galaxy follows a hyperbolic trajectory through the solar system. They varied the time of perihelion, the moment of closest approach to the Sun, across all possible dates, effectively asking the question, if this object could have arrived at any time, what is the chance that it would pass this close to Venus, Mars, and Jupiter? The calculation treats the close approaches as independent alignment events, each requiring a specific angular separation in heliocentric longitude, the position of the planet along its orbit relative to the object's path. For Mars, the longitudinal separation at closest approach was approximately 10.8 degrees, for Venus, 14.5 degrees, for Jupiter, 11.2 degrees. These separations define windows of opportunity. If the object had arrived 1 week earlier or 1 week later, the planets would have been in different positions, and the encounters would not have occurred. The probability of Mars being within 10.8 degrees of the required position is 6.0%. The probability of Venus being within 14.5 degrees is 8.1%. The probability of Jupiter being within 11.2 degrees is 6.2%. These are individual probabilities. To find the probability of all 3 alignments occurring simultaneously, you multiply them together. The result is 0.03%, approximately 3 in 10,000, odds of 1 in 3,325. This is not impossible, but it is improbable enough to notice. Now add the conjunction timing. The perihelion of 3I Atlas occurs on October 29, 2025, at a moment when the object lies at a solar elongation of 12.8 degrees as seen from Earth. This places it deep in the forbidden zone, unobservable due to solar glare. If we define the conjunction window as any perihelion occurring within 30 degrees of solar elongation, a threshold that includes the period of practical unobservability, the probability of this alignment is approximately 16.7%. 1 in 6, not particularly rare by itself. But now combine the 2 probabilities. The chance that an interstellar object arrives with both the 3-planet alignment and the conjunction timing is 0.03% multiplied by 16.7%. The result is 0.05%, 5 in 100,000. Odds of 1 in 20,000. This is where coincidence begins to strain as explanation. If you were to simulate 20,000 random interstellar trajectories, only one would achieve this combination of planetary flybys and perihelion concealment. We are not claiming this proves artificial origin. We are claiming that the path is anomalous enough to justify scrutiny. And when you combine this trajectory with the other anomalies, the chemical composition, the age, the nickel emissions, the pattern becomes harder to dismiss. The path is not merely improbable, it is optimal. Consider what this trajectory accomplishes. By arriving nearly aligned with the ecliptic, the object maximizes its interaction time with the planetary system. A steeply inclined trajectory would pass through the ecliptic plane once, spending most of its time far above or below the planetary orbits. A low inclination trajectory like this one remains in the plane, threading between the orbits of multiple worlds. This is the geometry of reconnaissance. This is the path you would choose if you wanted to survey the inner solar system, passing close to multiple targets in sequence. By timing its arrival such that perihelion coincides with solar conjunction, the object ensures that the moment of maximum thermal and gravitational interaction, the moment when any propulsive maneuver would be most efficient, occurs when observation is impossible. This is the geometry of concealment. This is the timing you would choose if you wanted to act without oversight. By selecting a hyperbolic excess velocity of 58 kilometers per second, the object arrives fast enough to traverse the inner solar system in a matter of months, minimizing exposure time and reducing the window for detailed observation. A slower object would linger, allowing more opportunities for study. A faster object would pass too quickly for multiple planetary encounters. The velocity of 3I Atlas is precisely calibrated to the scale of the inner solar system. It spends enough time to complete the sequence, but no more. These are not arguments for artificiality. These are observations of efficiency. The trajectory of 3I Atlas achieves multiple objectives with minimal redundancy. Whether this is the result of chance or design is a question we cannot answer with certainty, but we can acknowledge that the trajectory is consistent with intentional design. Let us examine what this path allows. The close approach to Mars on October 3rd occurs 26 days before perihelion. At this point, the object is still relatively cold, but it is beginning to activate as solar heating increases. The encounter places 3I Atlas within the observational range of Mars-based spacecraft, but these spacecraft are not designed for cometary observation. They are planetary science missions with fixed orbits and limited maneuverability. The instruments that imaged the comet did so opportunistically, capturing a few frames during a brief window. The data is valuable, but it is not comprehensive. We see the object, but we do not study it in detail. The close approach to Venus on November 3rd occurs 5 days after perihelion. By this point, the object has passed behind the Sun, executed whatever maneuvers or processes it was designed or evolved to execute at perihelion, and is now departing the inner solar system. The Venus encounter provides a second opportunity for observation, but again, there are no spacecraft in Venus orbit equipped with the instruments necessary for detailed cometary spectroscopy. The object passes, and we record its position, but we do not analyze its composition or trajectory changes with the precision required to detect subtle anomalies. The approach to Jupiter on March 16, 2026, occurs more than 4 months after perihelion, by which time the object will have cooled significantly and its activity will have declined. Juno may observe it, but Juno is a magnetospheric and atmospheric probe, not a comet-chasing mission. The data will be limited. By the time 3I Atlas reaches Jupiter, the critical phase of its passage is long over. The evidence of what occurred at perihelion, if anything occurred, will be buried in the object's past trajectory, unrecoverable without continuous observation, which we did not have. This is the elegance of the path. It provides multiple opportunities for detection, satisfying the expectation that an interstellar object should be observable, while ensuring that none of these opportunities coincide with the moments when detailed, high-resolution study would be possible. We see the object before perihelion, but it is not yet fully active. We see it after perihelion, but the critical moment has passed. We never see it during perihelion, because the Sun blocks our view. The result is a dataset that confirms the object's existence and general properties, but provides no basis for detecting deviations from natural behavior. If you were designing a trajectory to survey the inner solar system while minimizing the risk of detection or interference, this is the path you would choose. If you were an interstellar civilization sending a probe to gather information about a star system, you would want your probe to pass close to multiple planets, collecting data from each, while ensuring that the most critical phase of the mission, the perihelion burn, the energy collection, the probe deployment, whatever the objective might be, occurs in a location and at a time when the dominant intelligent species in the system cannot observe it. This is not evidence, this is architecture. Now consider the alternative hypothesis, that this trajectory is natural, the result of a comet ejected from a distant star system billions of years ago, drifting through the galaxy and happening to arrive at our solar system with this particular path. This hypothesis requires us to accept that the comet was ejected at a velocity and angle such that, after billions of years of perturbations from passing stars, molecular clouds, and the galactic gravitational potential, it arrived at our system nearly aligned with the ecliptic. It requires us to accept that its arrival time was such that Venus, Mars, and Jupiter were positioned correctly along their orbits to permit sequential close encounters. It requires us to accept that the timing of perihelion coincided with solar conjunction as seen from Earth, the dominant observational platform in the system. Each of these coincidences is possible, but they are independent variables. The probability of all of them aligning is the product of their individual probabilities, and that product is 0.05%, 1 in 20,000. You can argue that 20,000 interstellar comets have passed through the galaxy in the time since this one was ejected. You can argue that we have observed 3 interstellar objects so far, and one of them happens to have these properties, which is within the expected range of statistical variation. You can argue that we are pattern-seeking beings, predisposed to see design where none exists. All of these arguments are valid. None of them change the numbers. The trajectory is what it is, the probabilities are what they are, and the pattern is consistent with intent. The premeditated path is not proof of artificiality. It is evidence that if this object were designed, its trajectory is precisely what we would expect a designed object to follow. It achieves maximum interaction with minimal exposure. It surveys multiple targets while concealing its most critical operations. It exploits the geometry of the solar system and the limitations of our observational infrastructure with a precision that natural processes rarely achieve. If the 12-day plan is real, the trajectory is its foundation. The path determines the timing determines the opportunity determines the outcome. Without this trajectory, there is no plan. With it, the plan becomes possible. And possibility, in the absence of certainty, is what we are left to evaluate. The object is now on its way to Venus. It has already passed Mars. It will pass Jupiter in the spring of 2026, and at each of these encounters we will collect data. But the data we collect will tell us where the object is, not what it did. The answer to that question is hidden in the blackout, locked behind the sun during the 12 days between conjunction and re-emergence. The premeditated path brought the object to that blackout. What happens next depends on what the object was designed, or fortunate enough, to do when it arrived there. A plan requires an architect. This is the principle that moves us from mechanics to motive, from trajectory to intention. We have established that 3i Atlas arrives on a path that is statistically improbable, timed such that its most critical phase occurs in perfect darkness. But the path alone does not distinguish between chance and design. The architect reveals itself through the object's fundamental nature, through what it is made of, through what it does. You are not told, directly, that 3i Atlas is fundamentally different from every comet ever studied in our solar system. You are told instead that it is unusual, that it displays anomalies, that its composition is unexpected. These words are the language of scientific restraint. They mean something stronger. They mean that 3i Atlas violates the rules that govern comet behavior, and objects that violate natural rules do not arrive by accident. Begin with carbon dioxide. The coma of a comet, the cloud of gas and dust surrounding its nucleus, is primarily composed of water vapor and carbon monoxide in ratios that have been measured and catalogued across hundreds of observations. These ratios are not random. They reflect the temperature history of the object, the distance from which it originated in its parent star system, and the physical processes that shaped it billions of years ago. When astronomers measure a comet's composition, they are reading a geological autobiography. The ratios tell the story of formation. 3i Atlas tells no conventional story. On August 6, 2025, the James Webb Space Telescope observed 3i Atlas from a heliocentric distance of 332 AU. using its NIR-spec infrared spectrograph, JWST measured the molecular content of the object's coma across wavelengths from 0.6 to 5.3 micrometers. The data revealed a carbon dioxide to water mixing ratio of 8.0 1.0. This number requires context. In typical solar system comets, objects that formed with our Sun and planets 4.6 billion years ago, the CO2 to water ratio varies between 0.1 and 2.5. At the heliocentric distance where 3I Atlas was observed, models predict a CO2 to water ratio of approximately 0.48. The measured value of 8.0 is 16 times higher than predicted. It is 6.1 standard deviations above the trend line established by 2 centuries of cometry spectroscopy. In statistical terms, this is not an anomaly, it is an impossibility. Consider what this means. The abundance of carbon dioxide in a comet's ice is determined by the chemical conditions during its formation. CO2 ice forms through reactions between carbon monoxide and hydroxyl radicals on grain surfaces, primarily during the dark, cold phase of star formation. Water ice forms through a competing process, the hydrogenation of hydroxyl radicals. Under normal conditions, the water formation pathway dominates. CO2 requires special circumstances. It requires exposure to intense ultraviolet radiation or cosmic rays that suppress the water-forming pathway, or it requires formation in a region of the disk so cold and so far from the parent star that CO2 accumulates preferentially. A comet with a CO2 to water ratio of 8.0 implies either one of 2 scenarios. The first, 3I Atlas, formed in a disk so highly irradiated, so scarred by stellar radiation, that the chemical equilibrium shifted fundamentally towards CO2 production. The second, it formed beyond a CO2 frost line, in a region of planetary formation so distant and so cold that carbon dioxide, not water, was the dominant ice. Both scenarios are physically possible. Both are also extremely rare. To find a natural comet displaying this composition requires either an exceptionally violent young star system or an exceptionally distant formation region. 3I Atlas tells us it does not care which. The object arrived with what it arrived with. But here is what makes the chemistry truly unsettling. The mixing ratio of carbon monoxide to water in 3I Atlas is 1.402. This is entirely normal. It matches the predictions for comets at this heliocentric distance. It matches the ratios observed in other interstellar objects. In other words, one mixing ratio is spectacularly anomalous and the other is utterly unremarkable. This is not how natural systems typically behave. When an object's chemical composition is determined by its origin environment, multiple ratios should be anomalous, or multiple ratios should be normal. They should correlate. The fact that the COA-H2O ratio is normal while the CO2O ratio is extreme suggests a decoupling. It suggests that something in the object's recent history has preferentially depleted one compound or enriched another, independent of formation conditions. The simplest explanation, the nucleus has a crust, an insulating crust different in composition from the interior, a crust that inhibits the sublimation of water while allowing carbon dioxide to escape freely. Such a crust would explain the anomalous CO2-H2O ratio, it would explain the normal COA-H2O ratio, and it would raise the question, how does a comet acquire such a crust naturally? Cosmic ray irradiation during interstellar transit can modify the composition of a comet's surface layer. This is known. But the effect is typically limited to depths of micrometers, not the tens or hundreds of meters that would be required to suppress water sublimation at 3.32 AU. A thicker, more substantial barrier, something more like a volatile depleted mantle, a processed shell layered over unprocessed ice, would be required to produce the observed effect. Such a structure could form naturally if a comet underwent heating and surface sublimation cycles before being ejected into interstellar space. It could also be engineered. A designed probe entering interstellar space would benefit from thermal regulation. An insulating crust would protect the interior from cosmic radiation. It would preserve the object's propellant and energy reserves for the critical moment when they are needed. Now turn to the metals. In July 25, observers using the Very Large Telescope in Chile detected atomic nickel in 3I Atlas's coma. Nickel emission is not unusual in comets. Many objects display detectable nickel vapor as they approach the Sun. What is unusual is what the VLT observers did not detect. They did not detect iron. Iron and nickel are sister elements. They form in the same stellar nucleosynthesis processes. They arrive in the solar system in similar abundances. In the dust of protoplanetary disks, the iron-to-nickel ratio is approximately 1:0, equal amounts of both metals. When comets are heated by solar radiation, both metals sublime into the coma in roughly proportional amounts. This is the expectation established across centuries of observation. This is the rule. 3I Atlas violates it. By August 25, 2025, the VLT measured nickel production rates of 4.607 grams per second. This is extraordinarily high. Scaling to a heliocentric distance of 1 AU using standard sublimation models, this yields a nickel production rate of approximately 3.8281 cm1 mies 9 mides atoms per second, a rate that exceeds famous comets like Hyakutake, one of the most active comets observed in the past century. Yet no iron was detected. No iron vapor appeared in any spectral line. The nickel-to-iron ratio was effectively infinite. Chemists speculate that nickel may be released from organic compounds called nickel tetracarbonyl and iron pentacarbonyl, metal-bearing molecules that decompose when exposed to solar ultraviolet radiation. Both compounds sublime at similar temperatures. Both are present in typical cometary ices, yet somehow in 3I Atlas, the iron-bearing compound decomposed little or not at all, while the nickel-bearing compound decomposed vigorously. This is chemically suspicious. When two compounds have similar sublimation temperatures and similar thermal stability, they should decompose at proportional rates. The fact that one dominates so completely suggests either an unusual bulk composition or a deliberate separation of components. Consider the implications of deliberate separation. Nickel is a superconducting element. At cryogenic temperatures, certain nickel alloys exhibit extraordinary electrical properties. Iron, by contrast, is ferromagnetic but lacks superconductivity. If an architect wished to construct a probe that required electromagnetic manipulation or energy collection at near solar temperatures, nickel would be the superior choice. An object designed to operate near the Sun, relying on electromagnetic systems for maneuvering or power generation, would benefit from nickel abundance. It would have reason to minimize iron abundance, which produces thermal drag through ferromagnetism and unwanted electromagnetic interactions. This is not evidence. This is architectural reasoning. Now add the age to the profile. In July 2025, dynamical modeling of 3I Atlas's galactic kinematics, the trajectory backward through the Milky Way's gravitational field, suggested an object age of between 7.6 and 14 billion years. The solar system is 4.6 billion years old. The universe is 13.8 billion years old. 3I Atlas is older than our solar system. It may be as old as the universe itself, or nearly so. This age estimate comes from studying the object's velocity components relative to the galactic center and the galactic plane. The high vertical velocity, motion perpendicular to the disk of stars, indicates that 3I Atlas belongs to the galactic thick disk, a population of ancient stars that orbit in elongated paths above and below the galactic plane. The thick disk formed early in the Milky Way's history, roughly 13 billion years ago. Objects that originate there are typically ancient. an object 7.6 billion years old, ejected from a young star system in the early galaxy, has been in transit through interstellar space for an enormously long time. It has been exposed to cosmic rays, solar wind particles from passing stars, and the erosive effects of the interstellar medium. The surface of such an object would be heavily damaged. The volatile ices would be partially depleted, irradiated, and transformed into more complex organic compounds. The object would present a dark, weathered appearance. It would be spectroscopically atypical. 3I Atlas is spectroscopically atypical, but it is atypical in a direction opposite to what cosmic ray irradiation predicts. Its composition is not what you would expect from 7.6 billion years of space weathering. Its coma composition, the CO2 dominance, the nickel abundance, the organic compounds, suggests either that the object was recently refurbished, its surface recently stripped away to reveal fresh material, or that it is being preserved in a state inconsistent with its age. This is the profile of the architect. An object that is ancient enough to predate the solar system. An object that originates from a region of the galaxy extremely distant from Earth. An object whose composition defies the standard models of comet chemistry. An object whose trajectory passes improbably close to multiple planets while achieving perfect invisibility during its critical phase. An object whose surface exhibits signs of recent processing or deliberate engineering. An object composed of materials, carbon dioxide ice, nickel alloys, volatile depleted crust, that would serve the needs of an advanced technological probe far more efficiently than they serve the needs of a simple comet. These are not coincidences, these are specifications. To build a probe that must traverse the galaxy for billions of years, you would want it to be ancient, or you would want it to be able to pretend to be ancient. You would shield it from radiation with an insulating crust. You would optimize its composition for electromagnetic systems by favoring nickel over iron. You would design its trajectory to pass through multiple planets in sequence, gathering data or executing some other objective. You would time its entry into the solar system to achieve a critical maneuver during a period of total observation blackout. Every characteristic of 3I Atlas aligns with these specifications, not all of them, all of them. The chemical composition, the age, the trajectory, the timing, the metallic ratios, the coma structure. Every single measured property points toward an object designed rather than discovered. You will be told that this is coincidence. You will be told that the object is a natural comet that happens to be anomalous in several independent ways. You will be shown statistical arguments that such anomalies, while rare, are not impossible. These arguments are technically correct. They are also diversions from a more fundamental observation that at some point the accumulation of improbabilities ceases to be coincidence and becomes pattern, and pattern ceases to be pattern and becomes purpose. The architect of 3I Atlas made choices. The object is the physical manifestation of those choices. Whether the architect is biological or synthetic, whether it originates from our universe or another, whether it has been traveling for 6 billion years or merely appears to be ancient to explain its presence, these are questions we cannot answer with certainty. But we can say this with confidence: the object before us is not a wandering comet from the wreckage of a distant star system. It is something that was constructed, it is something that was sent, and it is something that has just completed the first stage of a plan that human observers were not meant to detect. The profile tells us this: the evidence does not lie. It merely awaits interpretation by those willing to ask the questions that institutions will not. We have established the plan. We have established the premeditated path. We have profiled the architect. Now we arrive at the question that institutional science refuses to articulate directly. What is the object trying to do? We cannot answer this with certainty. We can only construct a framework of plausible objectives, each consistent with the trajectory, the timing, the chemistry, and the physics. Each mission profile we will examine requires 3i Atlas to achieve certain things during the 12-day window of invisibility. Some of these objectives are mutually exclusive. An object cannot simultaneously harvest maximum energy and execute a braking burn, but an object can accomplish multiple objectives sequentially, and the 12 days provide sufficient time. Begin with the clandestine maneuver. The phrase braking burn describes a specific propulsive action, the firing of thrusters in the direction opposite to the object's motion, reducing its velocity. For a spacecraft approaching a gravitational body at hyperbolic velocity, a braking burn is the mechanism by which it transitions from an escape trajectory to a bound orbit. The most efficient place to execute such a burn is at perihelion, where the object is moving fastest. This is the Oberth effect in reverse. At perihelion, 3i Atlas travels at 58 km per second relative to the Sun. The local escape velocity at this distance is 36.12 km per second. The hyperbolic excess velocity, the velocity above escape, is 38 km per second. To transition from this hyperbolic trajectory to a circular orbit at perihelion distance would require a retrograde delta V of approximately 45.4 km per second. This is not impossible, it is merely expensive in terms of propellant. Or it is inexpensive if the object possesses a high specific impulse propulsion system, nuclear thermal, nuclear electric, antimatter annihilation, or any of the exotic drive systems theorized for advanced spacecraft. The specific impulse of such systems far exceeds chemical rockets. A single-stage spacecraft equipped with a nuclear engine could execute a 45 km/s burn at perihelion with a propellant fraction below 50%. That is, less than half the object's dry mass need be dedicated to propellant. If 3i Atlas is composed primarily of volatiles, water ice, carbon dioxide ice, organic compounds, the remaining rocky nucleus could be engineered to contain both propulsion systems and payload. The nucleus, with an estimated radius of 5 km and a bulk density of 800 to 1,000 kg, contains enough mass to fuel such a maneuver, provided the propulsion systems are sufficiently advanced. The Oberth effect guarantees that a burn executed at perihelion produces maximum velocity change per unit propellant consumed. A retrograde burn at perihelion would reduce the object's hyperbolic excess velocity from 4 km to something less. A delta V of 10 km would reduce excess velocity to 35.4 km, still hyperbolic but shallower, lengthening the object's trajectory. A delta V of 20 km would reduce excess velocity to 25.4 km. A delta V of 45.4 km would reduce excess velocity to 0, capturing the object into a circular orbit at perihelion distance, roughly 1.36 AU from the Sun. Any of these braking burns would be invisible from Earth. The thermal signature would be masked by solar radiation at the object's distance from the Sun. The exhaust plume would be indistinguishable from natural cometary outgassing. Spectroscopic observation during the visibility windows would reveal nothing anomalous, because we would be examining the object's composition after the burn, not during it. The purpose of a braking burn would be to slow the object's departure velocity, changing its trajectory to remain in the solar system rather than escape. This serves reconnaissance objectives. An object that remains bound to the Sun can complete multiple orbits, gathering information over years or decades. An object that escapes can only gather information during its single pass through the system. The difference is strategic. It is the difference between a survey mission and a one-time reconnaissance probe. This leads to the second objective, energy capture. At perihelion, the solar radiation flux is 736 watts per square meter, more than half the intensity at Earth's orbital distance. For an object with the cross-sectional area of 3i Atlas, approximately 78.5 square kilometers, based on an estimated nucleus radius of 5 kilometers. The total solar radiation intercepted is approximately 57 gigawatts. This is an enormous amount of power. In principle, this power could be harvested. A light sail constructed from reflective material, thin enough to deploy and compact enough to store aboard a probe, could capture solar radiation pressure, converting photon momentum into propulsive force. The object could unfurl such a sail at perihelion, allowing the intense solar radiation to accelerate it, increasing its velocity as it departs the inner solar system. This would be energy capture, in the sense of radiation pressure propulsion. Alternatively, thermal energy from solar radiation could be converted to electrical energy through high-efficiency thermoelectric systems or through solar to heat to electricity conversion. The captured energy could power propulsion systems, communication systems, scientific instruments, or energy-intensive manufacturing processes. An object designed to operate for billions of years in the cold of interstellar space would require energy. The perihelion passage provides an opportunity to charge batteries, supercapacitors, or radioisotope thermal systems for use in the years following the encounter. Energy capture has no visible signature. The process produces no emissions. It is silent. It is perfect for concealment during the invisibility window. An object that harvests the sun's energy at perihelion and stores it for use in later phases would appear, upon re-observation, to be simply a comet that has been heated by proximity to the sun. The spectroscopic signatures would be consistent with thermal processing of ices and organics. We would attribute the appearance to natural heating, not to deliberate energy extraction. This leads to the third objective, probe deployment. An object traveling at hyperbolic velocity cannot simply release secondary payloads and expect them to remain nearby. Any probe separated from the parent body inherits the parent's velocity. To achieve a different trajectory, the probe must be provided with an independent propulsion system or released from the parent such that natural perturbations alter its subsequent path. However, if the parent object executes a braking burn at perihelion, reducing its velocity, then secondary probes released after the maneuver would travel at the new, reduced velocity. The differential velocity between parent and probe would be small, sufficient to separate them without requiring excessive delta V. Multiple probes could be deployed in sequence, each with slightly different release timing, allowing them to enter divergent heliocentric orbits that would eventually place them in different solar system locations: Mars orbit, Venus orbit, Earth orbit, or interstellar space beyond. The advantage of deploying probes after a braking burn is that the probes inherit the parent body's reduced velocity, making them easier to target towards specific planetary orbits. A probe released from a hyperbolic trajectory approaches Venus or Mars at extreme velocity, tens of kilometers per second, making capture or close approach difficult. A probe released after a braking burn approaches at much lower velocity, allowing simpler orbital insertion or flyby trajectories. Furthermore, probes deployed from the interior of a comet after a braking maneuver would emerge surrounded by cometary dust and outgassing material. They would be nearly invisible to external observation. To an external observer, the object would appear to be undergoing normal cometary fragmentation or outbursts. The probes would be indistinguishable from internal fragments and dust clouds. By the time the outer coma clears and the probes become theoretically observable, they have already begun their divergent trajectories toward their destinations. This is the elegance of the deployment strategy. The parent object provides propulsion, guidance, and concealment. The probes disperse at precisely the right moment, when observation is impossible and when their separation from the parent would appear natural. What would these probes do upon arrival at Mars, Venus, or Earth orbit? This is where speculation enters, because we have no direct evidence. But mission profiles exist. Scientific reconnaissance probes could survey planetary atmospheres, collect atmospheric samples, study magnetospheres, or image surface features from orbit. Engineering probes could assess planetary resources, study geological composition, or evaluate surface conditions for future landing operations. Military reconnaissance probes could establish persistent observation networks. Communication relay probes could establish communication infrastructure for future missions. Any of these activities would be served by probe deployment during the perihelion phase of the 3I Atlas encounter. The probes would arrive at their destinations weeks or months after deployment, by which time the parent body would be far distant. The connection between the deployed probes and 3I Atlas would be undetectable by standard astronomical methods. We would identify the probes only when they revealed themselves, if they chose to do so at all. Now combine these three objectives: the clandestine maneuver, energy capture, and probe deployment. An object arrives at perihelion. It remains invisible for 8 days. During this time, it executes a retrograde braking burn, reducing its velocity from 58 kilometers to some lower value, perhaps 48 kilometers, perhaps 38 kilometers, perhaps lower still. The delta V required depends on the desired outcome. A 10 kilometers burn requires perhaps 1 to 2% of the object's total mass in propellant, assuming advanced propulsion technology. A 20 kilometers burn requires perhaps 4 to 5%. A 45 kilometers burn to achieve orbit requires perhaps 40–50%. While the maneuver is executing, the object simultaneously deploys a light sail or thermal collection system, harvesting energy from the intense solar radiation field. The captured energy supplements the propulsion system, reducing propellant consumption. Every bit of solar energy converted to kinetic energy is propellant saved. As the braking burn completes, thermal stress from proximity to the Sun causes the outer layers of the nucleus to fracture and shift. This natural disruption provides concealment for probe deployment. Secondary payloads, pre-positioned within the nucleus, are released into the cometary coma. They emerge surrounded by dust and fragment debris, invisible against the background of natural outgassing material. Within hours, the parent body's velocity has changed. Within days, the probes have separated sufficiently to develop independent trajectories. Within the remaining days of the invisibility window, the configuration stabilizes. The parent body, now on a modified trajectory, and the probes, now on their divergent paths, are all invisible to external observation. The solar conjunction that enabled their concealment now ensures that no one on Earth can see what has occurred. On November 14, 2025, when 3I Atlas re-emerges from solar conjunction, we will see a comet. Spectroscopic analysis will show composition consistent with our previous observations. The dust tail will show brightening consistent with thermal heating. The coma will expand and contract as outgassing continues. Everything will appear natural. And we will never know that the object's trajectory has changed, that its velocity has been reduced, that secondary payloads were deployed, or that the primary objective has been accomplished. This is not prediction. This is description of what becomes possible when an object with these characteristics at this distance from the Sun, during this window of invisibility, possesses the engineering sophistication to execute these maneuvers. Whether 3I Atlas actually executes these objectives remains unknown, but the possibility exists. And possibility, undetected and unconfirmed, is the most dangerous kind. There is a fourth objective we must consider: communications relay and transmission. An object positioned at perihelion, 1.36 AU from the Sun, is positioned to broadcast information or receive commands across interstellar distances. The intense solar radiation at perihelion could be modulated to carry information. Modulating the outgassing pattern of the comet would create variations in the scattered light, which could encode information for distant receivers. Alternatively, Coherent radio or laser signals could be broadcast into space, their direction and frequency engineered to reach distant targets, potentially other interstellar probes, potentially receiver stations in orbit around planets, potentially civilization somewhere beyond the solar system. The invisibility window provides perfect concealment for such communications. Any radio signal or modulated light emission from the object would be blocked from Earth-based observation by solar glare. Any incoming signals received by the object would be similarly hidden. Communications could occur completely outside our detection capability. This objective requires no visible manifestation, no emissions we can detect, no propulsion signature, no energy consumption beyond what a designed probe would naturally require for its communication systems. A communications relay operates silently, and its operation during solar conjunction would be undetectable. What distinguishes this scenario from natural comet behavior is that it requires intentionality. A natural object does not broadcast signals. A natural object does not wait for communications windows. A designed object does both. If 3i Atlas is acting as a communications relay or transmission platform, it is doing so with perfect concealment during exactly the window when such activities would be hardest to detect. The central thesis of this section is that 3i Atlas, during its 12-day invisibility, could accomplish any or all of these objectives, executing a braking burn to modify its trajectory, harvesting solar energy to power its systems, deploying probes to multiple locations in the solar system, and broadcasting or receiving communications across interstellar distances. None of these activities would leave detectable signatures. None would violate known physics. All would serve strategic objectives consistent with an advanced technological civilization's interest in our solar system. We cannot prove these objectives are being pursued. We can only observe that the object's arrival trajectory, timing, and composition are consistent with their pursuit. And consistency across multiple independent parameters moves beyond coincidence. It approaches the realm of pattern. And pattern, once established, demands explanation beyond dismissal. When 3i Atlas re-emerges in November, we will resume observation. We will measure its spectrum, its trajectory, its outgassing rate. We will compare the data to our earlier observations and to models of comet behavior. We will analyze the results with scientific rigor, and if nothing unusual is detected, we will conclude that nothing unusual occurred. This is the limitation of science when confronted with concealment during observation blackout. The absence of detection is not the absence of event, it is merely the successful implementation of the plan. When an institution encounters evidence that challenges its fundamental assumptions, it does not typically announce this openly. It does not issue press releases acknowledging uncertainty. It does not admit that its models may be inadequate. Instead, it manages the narrative. It controls the flow of information. It frames the anomalous as routine, the unprecedented as expected, and the inexplicable as merely complex. This is not conspiracy. This is institutional behavior. The response to 3i Atlas follows this pattern precisely. Begin with the silence. Within hours, automated detection systems had alerted observatories worldwide. Within days, preliminary spectroscopic observations had begun. Within weeks, the chemical anomalies had been detected, the CO2 dominance, the nickel emissions, the absence of iron. These are significant findings. They represent discoveries that challenge our understanding of cometary composition and interstellar object behavior. Yet for the first 6 weeks following discovery, NASA issued no comprehensive public statement, no press conference, no detailed briefing for the scientific community. The object was mentioned in routine astronomical bulletins described as the third interstellar object and posing no threat to Earth. The language was carefully neutral. The tone was deliberately reassuring. The public was informed that the object existed, that it was being monitored, and that it was not dangerous. they were not informed that it was unlike anything previously observed. The European Space Agency followed a similar protocol. ESA's initial statements, released in late July, emphasized the agency's rapid response and global cooperation. ESA reacted promptly to the discovery, they reported. ESA astronomers began using ground-based telescopes in Hawaii, Chile, and Australia to monitor its progress. The language focused on competence and coordination. It did not focus on the object's anomalous properties. This is standard institutional messaging when confronting an unprecedented situation. Emphasize capability. Minimize uncertainty. Do not speculate publicly about implications that cannot be controlled. By August, the pattern had intensified. The James Webb Space Telescope had observed 3I Atlas and detected its extreme CO2 to water ratio, 8.0 compared to the expected 0.5. This was a 6.1 sigma deviation from the established trendline. In statistical terms, this represents an event so rare that it should occur by chance less than once in 10 million observations. Such findings typically prompt immediate publication and widespread scientific discussion. Instead, the data was mentioned briefly in technical papers, described as unusual and unexpected, then buried in the broader context of routine interstellar object characterization. The Very Large Telescope detected nickel emissions without corresponding iron. This finding was even more anomalous. No natural process known to science preferentially sublimates nickel while suppressing iron sublimation at the same temperature. The discovery challenged basic models of metal chemistry in cometary environments. Yet when the finding was reported in September, it was framed as a surprising detection and an interesting chemical signature, not as evidence that contradicted established scientific understanding. This is linguistic containment. The findings are acknowledged but not emphasized. The implications are mentioned but not explored. The public receives information but not interpretation. The narrative remains controlled. By October, as perihelion approached, the messaging had evolved to address a new problem, the visibility gap. Amateur astronomers and independent observers had calculated that 3I Atlas would disappear behind the Sun during its most thermally active phase. This was not difficult to predict. Solar conjunction dates are straightforward to compute from orbital elements. Yet NASA's public communications did not emphasize this timing. They did not discuss what observations might or might not be possible during conjunction. They did not explain why the object would be unobservable during perihelion. When questioned directly about the conjunction timing, officials described it as a routine astronomical phenomenon. This is factually accurate but contextually misleading. Solar conjunction is routine for planets, which orbit the Sun on predictable schedules. It is not routine for interstellar objects, which approach from random directions at random times. The probability of an interstellar object reaching perihelion during conjunction is approximately 16.7%. Not impossible, but not routine. The language pattern is consistent. Acknowledge the fact, minimize the significance, avoid speculation about implications. On October 21, 2025, the exact date 3I Atlas entered solar conjunction, the International Asteroid Warning Network announced a training exercise focused on the object. This announcement requires careful analysis. IAWN describes itself as a global coalition of astronomers, observatories, and planetary defense organizations. Its mission is to detect and monitor potentially hazardous objects in space. The organization conducts routine observational campaigns to test detection and tracking capabilities. These campaigns are typically announced months in advance. They target objects with well-understood orbits and predictable behavior. The 3I Atlas campaign was different. It was announced on the day the object became unobservable. It was framed as an observational exercise, but scheduled for November 27 to January 27, 2026, the period when the object would be departing the inner solar system, long after its most interesting phase had concluded. The stated objective was to enhance the community's ability to gather precise astrometric data, a technical goal that would be better served by observing the object when it was brighter and more active, not when it was dim and distant. The timing and framing suggest that the campaign serves a different purpose than the stated one. It provides institutional justification for intensive monitoring of the object during the period when it reappears from conjunction. It allows global observational resources to be focused on 3I Atlas without explicitly acknowledging that the object's behavior during conjunction might have been unusual. It creates a framework for data collection that appears routine, but enables detection of post-conjunction anomalies. This is anticipatory containment. If the object's post-conjunction behavior differs from pre-conjunction predictions, the discrepancy can be attributed to improved measurement techniques developed through the training exercise. If no discrepancies are detected, the exercise is simply routine capability building. Either outcome allows the narrative to remain controlled. Harvard astrophysicist A.V. Loeb responded to these developments with direct criticism. Loeb has a history of challenging institutional consensus on interstellar objects. He argued that Oumuamua's anomalous acceleration might indicate artificial origin. He has suggested that the scientific community is biased against considering non-natural explanations for unexplained phenomena. His statements about 3I Atlas follow this pattern. In interviews and published articles, Loeb argued that the object's characteristics, the chemical anomalies, the trajectory, the conjunction timing, warrant serious consideration of artificial origin. He criticized NASA for delaying the release of observational data, particularly images from Mars-based spacecraft. He suggested that the conjunction timing might be deliberate, allowing the object to execute maneuvers while hidden from Earth-based observation. He called the object a potential black swan event, a low-probability occurrence with high-impact consequences. The institutional response to Loeb's statements was swift and predictable. Space agencies emphasized that the object poses no threat to Earth. Scientific organizations stressed that natural explanations must be thoroughly investigated first. Media coverage focused on the controversy surrounding Loeb's speculation rather than on the observational data that prompted it. This is deflection through personalization. The focus shifts from anomalous data to controversial interpretation. The discussion becomes about scientific methodology and proper skepticism rather than about unexplained phenomena. The institutional narrative remains intact. Responsible scientists study the evidence carefully, while speculative scientists make premature claims about extraordinary explanations. But deflection does not address the underlying pattern. NASA's delay in releasing Mars Reconnaissance Orbiter data, ESA's carefully neutral language about unusual features. The IAWN training exercise announced precisely when the object became unobservable. The emphasis on natural explanations without acknowledging how unnatural the observations have become. These are not isolated decisions, they are components of a coordinated response. Institutions that discover something unprecedented face a dilemma. If they announce the discovery prematurely, they risk scientific embarrassment if later data provides conventional explanation. If they remain silent too long, they risk credibility loss when the information eventually emerges. The optimal strategy is controlled disclosure. Release the data gradually, emphasize uncertainty, avoid speculation, and maintain the possibility that conventional explanations will eventually be found. This strategy works when dealing with scientific anomalies that are genuinely ambiguous. It fails when dealing with phenomena that accumulate evidence pointing in a single, unprecedented direction. 3I Atlas represents such accumulation. Every new observation adds to the pattern rather than resolving the ambiguity, the CO2 dominance, the nickel without iron, the trajectory probability. The conjunction timing. The age and origin. Each finding individually can be dismissed as unusual but not impossible. Collectively, they form a coherent narrative pointing toward intentional design. The institutional response reveals awareness of this accumulation, the careful language, the delayed data releases, the emphasis on routine explanation for extraordinary circumstances, the defensive posture towards speculation about non-natural origins. These are not the behaviors of institutions confident that conventional science will eventually explain the observations. These are the behaviors of institutions managing a situation that has moved beyond their explanatory frameworks. Consider the counterfactual. If 3I Atlas was simply an unusual but natural comet, institutions would emphasize its scientific value. They would highlight the discoveries it enables about interstellar chemistry and early stellar formation. They would celebrate the insights it provides into planetary system evolution in distant parts of the galaxy. They would use it as an opportunity to demonstrate the power of international collaboration in astronomical research. Instead, they minimize its significance. They downplay the anomalies. They avoid speculation about implications. They frame intensive study as routine training exercises. They respond defensively to questions about artificial origin. This suggests awareness that the object challenges fundamental assumptions in ways that cannot be easily contained within conventional frameworks. The pattern of containment serves institutional stability, but it comes at a cost. If 3I Atlas is actually what the evidence suggests, an engineered probe from an interstellar civilization, then humanity's first confirmed contact with extraterrestrial intelligence is being managed through bureaucratic protocols designed for routine scientific discovery. The most profound event in human history is being treated as an administrative problem. The narrative is being controlled not to serve truth, but to serve stability. This is perhaps the most unsettling aspect of the entire episode, not that institutions might be concealing evidence of alien technology, though they might be, but that they might be incapable of recognizing such evidence even when it arrives, because their frameworks for processing information are designed to normalize anomalies rather than acknowledge paradigm shifts. The 12-day plan, if it exists, relies on this institutional paralysis. The architect of 3I Atlas, if such an architect exists, understands that human institutions will interpret unprecedented events through familiar categories. A probe will be classified as a comet. Deliberate maneuvers will be attributed to natural processes. Evidence of intelligence will be dismissed as unusual chemistry. The plan succeeds not by evading detection, but by relying on institutional inability to process what has been detected. When 3I Atlas reappears from conjunction in November, institutions will resume observation. They will measure its spectrum, plot its trajectory, analyze its behavior. If evidence of maneuvers is discovered, it will be attributed to outgassing forces. If probe deployment is detected, it will be classified as natural fragmentation. If energy collection signatures are found, they will be explained as thermal processing of volatile ices. Every anomalized, every unprecedented observation will be made to fit existing models. This is not conspiracy. This is how institutions function when confronted with information that threatens their foundational assumptions. They do not suppress the information, they reinterpret it, they do not hide the data, they contextualize it, they do not silence the debate, they manage it. The pattern of containment is complete. The data exists. The observations have been made. The measurements have been recorded, but the interpretation remains controlled. The narrative remains stable. The institutions remain intact. And if 3I Atlas was designed to test humanity's ability to recognize intelligence when it arrives, the results of that test are now clear. We saw everything, we understood nothing, we contained the implications, and we moved on. Tomorrow, October 29, 2025, at 11,047 Universal Time, 3I Atlas will reach Perihelion. By the time you read these words, the critical moment may have already passed. The object is behind the Sun, invisible to every telescope on Earth, executing whatever protocols were encoded into its trajectory billions of years ago, or doing nothing at all, simply sublimating ice and releasing dust as any natural comet would. We will not know which scenario occurred until the object reappears. On November 14, 2025, 3I Atlas will emerge from solar conjunction. Observatories worldwide will reacquire it in the pre-dawn sky, low above the eastern horizon in the constellation Virgo. The object's brightness is predicted to be magnitude 12 to 13, still too faint for naked eye visibility, but within reach of amateur telescopes. Professional observatories will begin intensive monitoring as part of the IAWN training exercise. Spectrographs will measure its composition. Astrometry will track its position. Photometry will record its brightness. The data will accumulate. And we will ask, what are we looking for? The answer determines whether we will recognize what we find. If 3I Atlas executed a braking burn at Perihelion, the evidence will appear in its trajectory. Astrometric measurements, precise determinations of the object's position against the background stars, will reveal deviations from the purely gravitational path predicted by pre-conjunction observations. These deviations are quantified as non-gravitational accelerations, forces that act on the comet in addition to solar and planetary gravity. For natural comets, non-gravitational accelerations arise from outgassing. As volatile ices sublimate from the nucleus surface, the escaping gas produces a rocket-like thrust. The magnitude of this thrust depends on the outgassing rate, the rotation state of the nucleus, and the distribution of active regions on its surface. Typical values range from 10.7 to 10.75 meters per second squared. Over the 45-day gap between the last pre-conjunction observation and the first post-conjunction observation, such accelerations produce velocity changes ranging from 0.4 meters per second to 39 meters per second. A 10 per second braking burn, the maneuver we hypothesized for orbit circularization, would produce a velocity change 10,000 times larger than natural outgassing. Such a change would be immediately detectable. It would be undeniable. It would demand artificial explanation. But the plan, if it exists, does not require such extreme maneuvers. A more modest burn, 100 meters per second, 500 meters per second, 1 kilometer per second, would accomplish strategic objectives while remaining within the envelope of unusual but explainable natural activity. This is the architecture of plausible deniability. Execute maneuvers large enough to matter but small enough to attribute to enhanced outgassing, asymmetric jets, or nucleus fragmentation. The institutional response will frame any detected anomaly as higher than expected but not unprecedented. The object will be described as unusually active rather than artificially propelled. The narrative will remain controlled. Spectroscopic observations will reveal whether the object's chemical composition has changed. Pre-conjunction measurements established a CO2 to water ratio of 8.0 and nickel emissions without corresponding iron. If post-conjunction spectra show the same ratios, this suggests either that nothing unusual occurred or that the unusual event did not alter surface composition. If the ratios have changed, if CO2 abundance has decreased, if water has increased, if new molecular species have appeared, this could indicate thermal processing beyond what natural perihelion passage would produce. But every change has a natural explanation. Increased water production? The crust has eroded, exposing fresh ice. Decreased CO2? The volatile rich surface layer has been depleted. New molecular species? Complex organics have been synthesized by solar ultraviolet radiation. The scientific literature provides frameworks for interpreting any observation within natural bounds. The question is not whether natural explanations exist. The question is whether they are sufficient. Photometric observations will track the object's brightness. Pre-conjunction, 3I Atlas, was magnitude 13. Natural models predict it will fade to magnitude 13.5 or 14 as it recedes from the Sun. If it instead brightens, if it reaches magnitude 12 or 11, this would indicate enhanced activity. Observatories would report an outburst, a sudden increase in cometary activity driven by subsurface ice exposure or structural changes in the nucleus. Outbursts are common in comets. They are natural. They are explainable. They are also consistent with energy release from internal systems activating at perihelion. The pattern will be identical regardless of the object's nature. A natural comet that experienced intense thermal processing at perihelion and a designed probe that executed mission protocols at perihelion will produce indistinguishable observational signatures. Both will show non-gravitational accelerations. Both will show spectral changes. Both will show brightness variations. The data alone cannot differentiate between them. Differentiation requires interpretation, and interpretation is shaped by institutional frameworks that favor natural explanations over unprecedented ones. Now consider the deployed probes if they exist. Our calculations show that secondary payloads released at perihelion with modest separation velocities would reach planetary orbits within days to weeks. A probe targeting Mars orbit would arrive by November 3, 2025, 5 days after perihelion. A probe targeting Earth orbit would arrive by November 10. A probe targeting Venus would arrive by November 25. These probes would be small. They would be cold. They would emit no light of their own. They would be invisible against the background of space unless they activated propulsion systems or communications arrays. And if they remained passive, if they simply coasted into position, waiting, we would never detect them. Our asteroid detection surveys are designed to find objects many kilometers across that reflect sunlight. A probe the size of a car, painted black, traveling on a trajectory that places it far from ecliptic survey zones, would pass unnoticed. Detection would occur only if the probe self-identified, a sudden radio transmission, a burst of visible light, a gravitational signature from proximity to a spacecraft. Absent such revelation, the probes could establish positions throughout the inner solar system, conducting observations, relaying data, or simply waiting for instructions from a source we cannot detect. This is the nightmare scenario for planetary defense. Not that an interstellar object arrives, we can detect arrivals. Not that it performs maneuvers, we can measure trajectories. But that it deploys secondary payloads that become part of the background, indistinguishable from the millions of asteroids, debris fragments, and untracked objects that populate near-Earth space. By the time we realize they are present, if we ever realize, they have been in position for months or years, accomplishing objectives we can only imagine. The human response to reappearance will be carefully calibrated. Space agencies will announce that 3I Atlas has been reacquired and that observations are proceeding as planned. Press releases will emphasize international cooperation and the value of the observational campaign for understanding interstellar objects. If anomalies are detected, they will be framed as scientifically interesting rather than paradigm-threatening. The language will remain neutral. The tone will remain measured. The public will be reassured that everything is under control. Behind the institutional facade, a different calculation will occur. If trajectory changes exceed natural bounds, if chemical signatures cannot be reconciled with thermal models, if brightness variations follow patterns inconsistent with cometary behavior, then private conversations will begin among senior scientists and government officials. These conversations will not be publicized. They will focus on risk assessment, strategic implications, and response protocols. The threshold for acknowledging artificial origin is extraordinarily high. Institutions will exhaust every natural explanation before considering alternatives. This is not obstruction. This is epistemic conservatism. Extraordinary claims require extraordinary evidence, and the evidence we gather from 3I Atlas, no matter how anomalous, will never quite reach that threshold. There will always be one more natural mechanism to test, one more model to refine, one more observation to collect before conclusions are drawn. And while we debate interpretations, while we publish papers and convene conferences and refine our models, the object will depart. By January 2026, 3I Atlas will be beyond Mars' orbit, dimming rapidly as it recedes into the outer solar system. By March, it will pass within 0.36 AU of Jupiter, providing one final opportunity for close observation by the Juno spacecraft. If fuel reserves permit, if mission priorities align, if the opportunity is not quietly declined. By mid-2026, the object will be magnitude 15 or fainter, accessible only to the largest telescopes. By 2027, it will fade from detection entirely, disappearing into the outer solar system at 58 kilometers per second, never to return. The window closes. The dataset becomes fixed, and whatever conclusions we draw will be drawn from incomplete information gathered during the limited periods when observation was possible, interpreted through frameworks designed for natural phenomena. If the 12-day plan was real, if the object executed maneuvers and deployed probes and accomplished mission objectives during the blackout, we will never prove it. We will suspect, we will debate, we will publish papers arguing both sides, but certainty will remain beyond reach. This is the final lesson of 3I Atlas. Not that we were visited by intelligence from beyond our solar system, though we may have been, but that our systems for detecting and interpreting such visits are inadequate. We are optimized to find natural objects and explain anomalous behavior through natural processes. When an object arrives that exploits this optimization, that uses our observational gaps and our interpretive frameworks against us, we are blind even when we see. The plan's next move is not the object's, it is ours. We can continue as we have, analyzing 3I Atlas within the frameworks that have served us for centuries, attributing every anomaly to natural processes, dismissing speculation about artificial origin as premature and unscientific. This path is safe, it is institutionally stable, it requires no paradigm shifts. It allows us to publish papers, advance careers, and maintain the structures that define professional astronomy. It also ensures that if we were actually visited by an interstellar probe, we will fail to recognize it as such. Or we can acknowledge what the data suggests. Not with certainty, certainty is not available, but with intellectual honesty. We can state clearly that 3I Atlas exhibits characteristics inconsistent with natural cometary origin, that its trajectory, composition, age, and timing form a pattern pointing toward intentional design, that the 12-day invisibility window provided perfect opportunity for maneuvers that would serve strategic objectives, that the institutional response has prioritized narrative control over transparent investigation. We can say these things without claiming proof. We can acknowledge that the evidence is circumstantial but compelling, that natural explanations exist but strain credibility, that the accumulation of anomalies crosses a threshold where dismissal becomes more implausible than consideration. This path is dangerous. It risks professional reputation. It invites ridicule. It challenges the conservative epistemology that protects science from premature conclusions. But it also allows the possibility that we are not alone, that intelligence exists beyond Earth, and that it has developed capabilities sufficient to send probes across interstellar distances to study our solar system. The choice is not between belief and skepticism. It is between frameworks. Do we interpret 3I Atlas through the framework of cometary science, forcing the observations into models designed for natural objects? Or do we interpret it through the framework of strategic reconnaissance, asking what an interstellar civilization would design if it wished to study our system while minimizing detection? The data fits both frameworks, but only one framework predicts the pattern we observe. Only one framework explains why every anomaly points in the same direction. Only one framework accounts for the timing, the trajectory, the chemistry, and the invisibility window as integrated components of a coherent strategy rather than as independent coincidences. Tomorrow, perihelion occurs. The plan, if it exists, reaches its execution phase. We will not see what happens. We cannot see. The sun blocks our view, exactly as the trajectory predicts, exactly as the timing requires, exactly as the plan ensures. In 2 weeks, the object reappears. We measure, we analyze, we interpret, and we choose which framework to apply. If we choose natural explanation, we will find natural explanations. Science provides them. The object will become another entry in the catalogue of interstellar visitors, unusual in some respects, interesting for study, but ultimately comprehensible within existing models. The anomalies will be explained. The pattern will be dismissed. The narrative will stabilize. And if we were wrong, if the object was actually a probe, if the plan was real, if intelligence was testing our ability to recognize it, we will never know. We will have seen everything and understood nothing. If we choose strategic framework, we will acknowledge uncertainty. We will state that the object may be natural or may be artificial, that the data allows both interpretations, that current observations are insufficient to determine which is correct. We will advocate for enhanced monitoring, for development of detection methods optimized for artificial objects, for institutional protocols that permit consideration of non-natural explanations when warranted. We will accept the possibility that we are being observed, that the observers are vastly more advanced than we are, and that our first contact may not be with signals we intercept, but with artifacts we misidentify. The plan's next move is not what 3i Atlas will do. We cannot control that. The plan's next move is how we respond to what it has already done. Whether we recognize the pattern, whether we acknowledge the implications, whether we allow ourselves to ask the questions that institutions discourage. In 1950, physicist Enrico Fermi asked, "If intelligent life is common in the galaxy, where is everybody?" The question assumes that contact occurs through signals, through communication, through intentional revelation. But intelligence capable of interstellar travel need not reveal itself. It can observe passively. It can design probes that mimic natural objects. It can exploit the fact that observers interpret anomalies through existing frameworks, that institutions resist paradigm shifts, that human civilization is optimized to see what it expects. Perhaps the answer to Fermi's question is not that they are absent. Perhaps they are here, have always been here, arrive regularly on trajectories we classify as natural, execute missions during observation blackouts, and depart before we realize what occurred. Perhaps 1i Oumuamua was reconnaissance. Perhaps 2i Borisov was verification. Perhaps 3i Atlas is escalation. Or perhaps they are all natural comets, unusual in some respects, but ultimately explainable, and the pattern we perceive is the pattern-seeking nature of human cognition applied to insufficient data. Both possibilities remain open. The data does not eliminate either. The choice between them is not scientific, it is philosophical. It is a choice about how we interpret ambiguity, about which uncertainties we accept and which we reject, about whether we allow the possibility of intelligence when the evidence is suggestive but not conclusive. The 12-day plan is complete. The object has reached perihelion. Whatever was designed to occur has occurred or has not occurred. We await reappearance. We await data. We await interpretation. And in that interpretation we will reveal not what 3i Atlas is, but what we are. Whether we are a civilization capable of recognizing intelligence when it visits, or whether we are a civilization so committed to existing frameworks that we will normalize any anomaly, explain any deviation, and dismiss any suggestion that we are not alone. The plan succeeds not by avoiding detection. It succeeds by ensuring that detection changes nothing. That we see but do not recognize, that we measure but do not interpret, that we gather evidence but reach comfortable conclusions. On November 14, the object reappears. The observations resume. The analysis begins. And the next chapter of this investigation? Whether it is the investigation of an unusual comet or the investigation of humanity's first confirmed contact with extraterrestrial intelligence, will be written by those who choose which questions to ask. Ask the right questions, and the data speaks clearly. Ask the wrong questions, and the truth remains hidden in plain sight. The plan's next move is ours. In every corner of the universe we can observe, from the crust of ancient meteorites to the heart of dying stars, certain patterns repeat with unyielding regularity. One of the most consistent is the chemical partnership of iron and nickel, a duo forged in the terminal stages of stellar evolution and distributed together by the cataclysms of supernovae. It is a relationship written in the periodic table but scribed across the galaxies by the laws of physics themselves. In the vast archive of cosmic chemistry, these two metals have never been found to separate. Until now? The baseline is simple, though profound. In the cores of massive stars, nuclear fusion proceeds through increasingly heavier elements, hydrogen into helium, helium into carbon, carbon into oxygen, all the way up the chain to iron. Iron represents a crucial endpoint. Fusion beyond iron into nickel and heavier atoms stops being energetically favorable. It requires more energy than it yields, so the star's burning comes to a halt. In that moment, gravity wins. The star collapses, triggering a supernova, and the resultant explosion forges a cocktail of elements: iron, nickel, cobalt, manganese, copper, and a handful of even heavier atoms. The supernova's blast sends these freshly minted metals streaming into interstellar space in a fixed ratio, a fingerprint of the stellar processes that built them. Every rock sample ever analyzed, from carbonaceous chondrites that predate the solar system to lunar basalts retrieved by hand, confirms the rule. Iron and nickel are always found side by side, bound by geochemical and physical law. Whether in the metallic grains of asteroids or the icy cores of comets, the nickel-to-iron ratio hovers near 1:15. Not because chemistry conspires to manufacture twins, but because the universe offers no supply chain to separate them once fused. The chemistry of comets supports this verdict. As these bodies approach the sun, their ices sublimate, releasing gases and entrained dust. Among the vaporized material are atomic forms of iron and nickel driven into the coma by solar heat. Over decades of observation and hundreds of comets, astronomers have measured the atomic spectra of both elements flaring together in predictable, proportional quantities. Their dual presence is so established that a deviation would seem less an anomaly than a challenge to physics itself. With the appearance of 3I Atlas, that expectation collided with a stark new reality. In July and August of 2025, as the object swept toward Perihelion, the Very Large Telescope in Chile trained its spectrographs on its developing coma. The data returned in waves, more precise each night. They revealed a surging, unambiguous emission from atomic nickel, strong spectral lines, quantitatively persistent and consistent over several observation runs. But the iron lines, expected to accompany nickel as surely as shadow follows light, were simply not there. The longer astronomers looked, the clearer the void became. In every tested spectrum, iron was functionally absent, a ghost element in a chemical scenario that should have been impossible. No comet, asteroid, or meteorite in the solar system has ever shown such an imbalance. The ratio of nickel to iron in 3I Atlas, instead of clustering near 1:15, was incalculable. For all practical purposes, it was infinite. Presenting the anomaly as a simple oddity would be a failure of scientific honesty. What was observed is a violation, a breakage of the chemical rules that have applied universally, not just locally. The implication is not an error of measurement, but a disruption at the heart of cosmic chemistry. To account for the violation, official science proposed a daring hypothesis: nickel carbonyl, NiCoUd. On Earth, this molecule is a tool of industry, a colorless, highly toxic gas used principally to refine high-purity nickel from ore. Its controversial utility in industrial chemistry owes to its volatility at room temperature and its ability to decompose cleanly on contact with heated surfaces, leaving high-grade nickel behind. For nickel carbonyl to explain the absence of iron in 3I Atlas, the molecule must somehow be synthesized naturally in the interstellar medium, then incorporated into the comet's ices. The conditions required for this are rare and non-trivial. Nickel carbonyl forms at low temperatures and in the presence of abundant carbon monoxide, a combination found only in the darkest, coldest molecular clouds. It decomposes rapidly above 50 degrees Celsius, meaning it could persist only in deep space or deep within cometary ice, disintegrating only when freshly exposed to the sun's heat. This scenario would allow nickel to be liberated into the coma preferentially, while iron lacking a similar carbonyl remains locked in refractory grains. The numbers, in theory, could be made to add up. But they are theoretical numbers layered atop an extraordinary chain of coincidences. The industrial process that refines nickel on Earth bears no resemblance to anything in the solar system, let alone to anything in the void between stars. No nickel carbonyl has ever been positively identified in a comet's ices, nor modeled as a major phase in cometary chemistry until now, when explanation became necessity. Why does it matter? Because the result of this chemical selectivity is not merely a curiosity, but the creation of a material signature with profound technological advantages. Nickel is not just a mundane metal. In pure and alloyed form, it is the backbone of terrestrial and presumably extraterrestrial engineering. At cryogenic temperatures, nickel and its compounds can exhibit superconductivity, allowing for the perfect transmission of electric current, a property critical for quantum sensors, propulsion systems, and any technology where lossless energy flow is required. Its resistance to corrosion and strength at high temperatures make it vital for spacecraft designed to endure the fierce conditions close to stars. Alloyed with other metals, it becomes inconel, a material central to jet engines, rocket motors, and nuclear reactors. But its role as a conductor and controller of magnetic fields is perhaps most notable. Nickel is inherently ferromagnetic. In precisely patterned structures, it can be used to manufacture magnetic shielding, dense data storage, or even sophisticated electromagnetic propulsion systems. The ability to isolate nickel, free from iron, which can disrupt or dilute these properties, could represent a quantum leap in material science for any sufficiently advanced civilization. Given these facts, the nickel anomaly in 3I Atlas blossoms from a chemical curiosity into a signature of intent. If you sought to design a probe that could function in the extremes of interstellar space, you would want to construct it from elements that maximize durability, conductivity, and adaptability in electromagnetic fields, characteristics offered in abundance by pure nickel. If you had the ability to separate nickel from iron at astronomical scales, you could manufacture components with properties inaccessible to natural chemistry. Components capable of enduring cosmic rays, shifting magnetic fields, and the extremes of solar heating without degradation. You might even hide the telltale signature of your technology in a form that nature rarely, if ever, provides: pure, emission-ready nickel wrapped in a cometary disguise. Thus, the question becomes not, how did nature do this, but who would want to do this? When you find a material signature that cannot be explained by 14 billion years of physical law, you must entertain the possibility that it wasn't meant to be explained by them at all. The alternative is unsettling because it inverts the narrative of cosmic discovery. For centuries, we have assumed that anomalies are simply gaps in our knowledge of nature. Faced with the nickel-iron separation in 3I Atlas, the more rational conclusion may be that nature's rules have been deliberately bent not by chance but by design. The ghost in the machine is not a spectre of error, but the trace of a hand writing a message in spectral lines. The question that remains, are we willing to read it? If the story of the nickel anomaly of 3I Atlas teaches us anything, it is the necessity of recognizing ghost signatures, not as relics of natural process, but as messages encoded by architects able to engineer at stellar scales and subtle enough to ensure that their handiwork is indistinguishable from the most confounding workings of chance until the system that observes it is capable of asking the right question. In the grand pursuit of astronomical truth, few investigations reach as far back or as deep as the quest to determine the true age and origin of an interstellar visitor. When it comes to 3I Atlas, the most fundamental narrative is not found in its shimmering coma or hyperbolic journey, but in a forensic timeline, a billion-year alibi inscribed in its velocity and its composition. If we can trust this alibi, we are witnessing a traveler older than Earth, a relic from the earliest epochs of our galaxy. But if that alibi breaks, we face a mystery that transcends mere chemistry or orbit dynamics, a mystery that calls into question the very authenticity of cosmic history. Galactic forensic science begins with motion. In the solar system, the orbits of planets, comets, and asteroids are familiar, looping ellipses carved out by the gravity of our Sun. But an object that does not belong, an interloper, moves differently. It echoes the gravitational signatures of ancient populations, vast groups of stars older than the Sun and settled in thick bands above and below the galactic plane. The Milky Way contains two principal stellar disks: the thin disk where stars like our Sun reside, young, blue and evenly spaced along the flat spiral arms, and the thick disk, a more ancient halo of redder stars tilted and puffed upward toward the galactic poles. When astronomers trace 3I Atlas's path backward through the solar system and beyond, they rely on proper motion, the precise measurement of its velocity components, not just its speed toward or away from us, but its upward drift relative to the Milky Way's plane. By running this motion backward through models of the galaxy's dynamics, they compare it to the known distributions for thin and thick disk objects. The findings are stark. 3I Atlas fits the fingerprint of the thick, disk-high velocity, steep inclination, and the kind of orbital parameters reminiscent of a star system born 10 billion years ago. It is as if the object carries papers signed by the universe itself. Every kilometer per second of its journey, every degree of its orbital tilt corroborates the claim, "I was born before the planets, before the Sun, before the current spiral arms had even formed." It's not just old, it's primordial. When physical modeling is run backward through the major epochs of galactic evolution, the result is an estimated age for 3I Atlas between 6 and 10 billion years. In practical terms, this means that when the Earth was still molten, when the first continents had not yet risen, and before life had any foothold, this object was already voyaging through interstellar space. To appreciate the scale, consider this: the age of our star is 4.6 billion years. The oldest rocks on Earth are barely older than 4.1 billion years. The oldest known fossilized life is less than 3.8 billion years old. In contrast, the thick disk of the Milky Way, and by inference 3I Atlas, was already ancient when our solar system was born. In galactic forensics, this forms a kind of ancient traveler narrative, a testimony of an odyssey that dwarfs the entirety of terrestrial history. But the cosmic timeline establishes more than age. It establishes expectation. In such a span, an interstellar object undergoes innumerable encounters with the hazards of the galaxy. The processes are collectively known as space weathering, and they are as relentless as they are transformative. Space weathering has three principal effects. First, cosmic rays. High-energy atomic nuclei traveling near the speed of light bombard the surface, breaking molecular bonds and generating a menagerie of secondary particles. Second, Particle erosion from interactions with interstellar gas and dust steadily scours the exposed surfaces, embedding noble gases and grinding away at crystalline structures. Third, UV radiation from passing stars and diffuse galactic background light drives the photochemistry of complex organics, turning simple hydrocarbons into tholins, rich, reddish polymers that coat the surfaces of everything old in the deep vacuum. Over billions of years, a truly ancient comet or asteroid develops a thick, inert crust, a patina of processed organic matter insulating the volatile ices and metals within. Models predict that comets older than 1 billion years should have lost most of their surface ices, or have them locked beneath tens of meters of protective slag, inert and unresponsive even to the heat of a close stellar encounter. The composition becomes homogeneous, dominated by refractory materials and complex radiolytic products. COS, one of the more volatile molecules, should be among the first lost, sublimated, or chemically transformed through extensive irradiation. Yet when astronomers observe 3I Atlas, they are greeted by contradiction. The object sports an active, COI-rich coma, an effervescent halo of escaping carbon dioxide, so vigorous and bright it rivals the outputs of younger, fresher bodies recently stirred by gravitational disruptions. Its coma, instead of being a mere ghost of its former self, bursts with activity not seen in most solar system comets, let alone any candidate for interstellar antiquity. Its ratio of carbon dioxide to water is 6 sigma above the expected value, a statistical impossibility for an object claiming such incredible age. The alibi, on the surface, is airtight. The velocity, trajectory, and orbital inclination all match an epoch older than Earth itself. The chemical and spectroscopic signature, however, demands the opposite, a fresher, more recently processed surface with abundant volatiles, the hallmarks of youth. These two narratives cannot both be true unless something extraordinary has occurred. How do astronomers reconcile the paradox? The broken alibi forces a series of alternative explanations, each implying something radical about the nature of the object or about the protocols humanity applies to cosmic anomalies. First, could 3I Atlas have undergone a dramatic surface refresh after most of its interstellar journey was complete? In principle, a close stellar encounter could strip away the accumulated crust, exposing deep, volatile layers. The gravitational tides near a passing star, or the violent shock of a supernova within dozens of light years, could theoretically shear away the inert shell. If this occurred within the last millions or tens of millions of years, the object could retain the formal kinematic signature of ancient origin while carrying the chemical fingerprint of youth. Alternatively, the object may have experienced collision with another body, a cometary fragment, rock, or icy asteroid somewhere in the galactic deep. Such an event would erode the surface, potentially mixing or expelling the outer layers and revealing newer material. But both explanations are problematic. The odds of a billion-year-old object encountering and being so thoroughly resurfaced by a large impact or a close passage within a star system are uncomfortably low. If it happened, one might expect to see traces, a non-spherical nucleus, evidence of fragmentation, or a peculiar dust signature. None has been definitively observed. The second alternative, a more unsettling what if, is the possibility that the age is itself a form of camouflage. In the most literal reading of all available data, 3I Atlas could be a much younger object, deliberately engineered or engineered by natural forces unfathomable to us to mimic the kinematic and chemical signature of an ancient traveler. If you had a reason to avoid attracting attention while conducting a reconnaissance mission in a foreign star system, you would want your probe to be nondescript, old, inert, with nothing to suggest activity or current purpose. The thick disk origin narrative would provide cover, acting as a cosmic disguise. This scenario is not mere speculation, it emerges from the behavior of some of the most advanced strategies in intelligence and counterintelligence. In human terms, a clandestine agent is most effective when concealed by both appearance and provenance. If a probe intended to observe Earth and the solar system, it could be programmed for interstellar slingshot maneuvers, utilizing centuries or millennia of kinematic preparation to establish the precise trajectory needed to blend in with ancient visitor populations. The billion-year alibi could be calculated and executed given access to sufficiently advanced propulsion systems and navigational intelligence. A synthetic traveler camouflaged as a primordial object would leverage every institutional bias in its favor. Astronomers would interpret its velocity and path through the lens of natural population statistics. Its composition, though anomalous, could be dismissed as active cometary behavior, or exceptional but still within theoretical bounds. Its timing and orbit would minimize the window for detection, timed for periods of solar conjunction and obscuration. But what if the converse is true? What if the object is genuinely ancient, but has undergone processes completely unfamiliar to us? Mechanisms of self-preservation, remote resurfacing, or even planetary flybys strategically used to renew its activity. Some researchers have toyed with the idea that interstellar comets might harvest solar energy, using gravitational assists to melt and reform their crusts, cycling their surfaces to retain volatile activity for tens of billions of years. The evidence for such mechanisms is thin. No confirmed interstellar object before 3I Atlas has shown the same blend of kinematic age and chemical youth. There is also the possibility that the surface refresh was orchestrated deliberately by extreme technological means. If the probe was constructed to endure for a billion-year mission, it could carry systems for periodic resealing, vaporization, or energy harvesting, designed to simulate the natural activity of younger comets. The Doppler profile, orbital velocity, and inclination would stay constant, preserving the age alibi, while the coma activity could be dialed up or down according to tactical necessity. If you want to study a fortress, you do not storm its gates. You infiltrate, you blend in, you send what cannot be resisted, disguised as cargo, masquerading as gift or relic. The Trojan horse is one of humanity's enduring metaphors, military cunning disguised as innocence. When you consider 3I Atlas in the context of probe deployment, the metaphor is not merely poetic, it is instructive. Imagine the strategy behind the arrival of an interstellar object, thousands of years in the making. The main body, the horse, is massive and deliberately conspicuous. It follows a trajectory calculated to generate interest but minimize suspicion, a path that draws eyes but channels attention toward routine scientific explanations. Inside, or perhaps embedded within the nucleus, are smaller, soldiers' secondary probes asleep in the darkness, waiting for the appointed moment to awaken. You are the observer. The main body appears to be an active, anomalous comet. It travels in a hyperbolic arc, brightening as it approaches the sun, plunging through perihelion, and then dimming as it exits the inner system. You watch, measure, catalogue its activity. The story, you believe, is that of an ancient interloper, a relic carrying the chemical memory of distant star systems. But the real story, concealed and undetectable, is that of a clandestine insertion. The deployment is not a random release, nor a routine fragmentation. It is a military and intelligence maneuver executed with the precision of orbital mechanics and the subtlety of cosmic camouflage. The solar conjunction, when the object passes behind the sun, is not merely an inconvenience for astronomers, it is the perfect drop zone, a region of dynamic cover where maneuvers can occur with minimal risk of detection. The sun's glare, overwhelming in every observable wavelength, screens out terrestrial and space-based observation. Radio interference and particle flux obscure signal and noise alike. Even the most sophisticated instruments are blinded at proximity. The timing is not accidental, it is the synchronization of engineering and reconnaissance. The gravitational dynamics at perihelion do the rest, providing the maximal energy for rapid trajectory changes, efficient separations, and the insertion of payloads into divergent orbital paths. Now profile the soldiers. What does technological logic suggest about their nature? First, they must be small and stealthy. Large bodies are easily detected by survey telescopes. The art of infiltration lies in minimizing cross-section, thermal output, and reflected light. A probe designed for clandestine observation might be no larger than a household appliance, painted with non-reflective radar-absorbent material. Its thermal signature would be cooled to match the temperature of space, radiating at frequencies lost in the cosmic background. Second, their trajectories would be non-conventional. Rather than following the ecliptic, they might execute gravity assists or directed burns that place them in orbits only briefly coincident with known asteroid populations, then drift into stable, dead zones regions where astrometric coverage is sporadic and anomalies pass undetected for years at a time. Third, their operational mode is likely passive intelligence gathering. They might deploy low-power sensors capable of capturing electromagnetic emissions from planetary communications, nuclear detonations, and other industrial signatures. Some could be equipped for more active tasks, probing atmospheres, sampling plasma, or even contacting the indigenous technology by transmitting signals when discovery is most advantageous. But the Trojan horse scenario borrows another idea from modern military strategy, the von Neumann probe. Instead of a simple observer, the probe could be designed to replicate, manufacture, or even modify its own behavior. With resource utilization capabilities, a self-replicating agent could harvest material from asteroids or planetary rings, constructing new units or adapting itself to changing environmental conditions. To imagine the implications is to expand the mission profile. A single interstellar arrival seeds the solar system with a handful of entities. Some lie dormant for centuries, others awaken and act. A network is established, invisible but persistent, capable of forming the basis for future operations. Data relay, further reconnaissance, even intervention should the need arise. The deployment zone, the sun's drop zone, multiplies the effectiveness of this strategy. The energy required to alter trajectories or impart separation to the probes is minimized thanks to the heightened velocity and gravity at perihelion. The cover of solar conjunction means that every step, every activation, every dispersion event occurs while the primary observer, Earth-based science, is blind. In practical terms, it's the difference between a high-risk airdrop over open terrain and a hidden insertion during a total blackout. Aftermath is always the test of a successful Trojan horse operation. The main object, 3i Atlas, exits the conjunction into view, perhaps altered, perhaps unchanged. Observers log its position, measure its spectrum, and analyze the tail for evidence of fragmentation. All looks routine, just as the horse rolled through the gates of Troy, welcomed as a curiosity, studied as a relic. But the soldiers, the probes, are already gone, separated and operating independently. Their escape velocity, transmitted through the Oberth effect, allows them to blend with local populations. Over days or weeks, they drift into their planned orbits, some circling Earth, others en route to Mars or Venus, a few perhaps on long-term trajectories toward the giant planets. Some might maneuver for direct monitoring of the Sun or the heliopause or other boundary structures of the solar system. The evidence for their existence would be, by design, minimal. Occasional non-gravitational accelerations in the parent's trajectory, small changes in brightness, or the onset of odd spectral lines framed as outbursts or dust ejection. The fragments themselves, if they are detected, would be dismissed as cometary debris, their non-reflective surfaces and artificial temperature profiles marking them as dark asteroids or cold boulders, uninteresting, unremarkable, unseen. Meanwhile, the intelligence mission begins. The silent observers, scattered in strategic positions, commence monitoring. Months pass, years. The solar system continues as always, only now the clandestine presence has become fact. A handful of probes, unknown and undetected, recording every signal, every atmospheric change, every industrial emission. The main object completed its ritual, a public spectacle of arrival, scientific attention and departure. But the true payload was always misdirection. The after-action report for humanity is one of misplaced confidence. The event is catalogued, the mission is judged benign, and the system scientific, institutional, public concludes the episode. This is the legacy of the Trojan horse. Not confrontation, but infiltration. Not discovery, but diversion. The history of military and intelligence operations shows that denial is as powerful as force and invisibility as durable as armor. The strategy rests on a simple idea. The best way to remain unseen is to hide among the familiar, activate during the blackout, and leave observers with only uncertainty. A final reflection then on mission profiles and planetary defense. What would it take to detect or even respond to such a deployment? Surveillance infrastructure orders of magnitude more sensitive than our current asteroid searches. Algorithms tuned to the possibility of passive, low-thermal, non-ecliptic movement. Openness to the idea that not every fragment is a chunk of inert mineral or ice. Above all, an institutional willingness to redefine business as usual, to treat Trojan horses not as myth, but as methodological cues. Until then, 3I Atlas's true mission may already be complete. The soldiers are deployed, the fortress is infiltrated. We watched the horse, not the army. And in the silence that follows, the fate of Troy is instructive, not because it foretells defeat, but because it demonstrates how the triumph of strategy always eclipses the brilliance of spectacle. If this scenario is correct, institutional science faces a formidable epistemic challenge. Forensic modeling is only as strong as the physical processes it assumes are universal. If there exists a class of engineered objects capable of mimicking ancient populations or of artificially regaining youth, then every element of cosmic history becomes suspect. Age, once thought to be irrefutable, becomes an unreliable witness. Composition, the supposed arbiter of truth, becomes a potential accomplice in a deception that spans the length and breadth of the Milky Way. The paradox becomes philosophical, not just technical. Can we ever truly know what we are seeing? Is 3I Atlas a genuine ancient traveler, a relic of the thick disk, surviving against all statistical odds with its volatile ices intact? Or is it a younger agent, disguised through kinematic camouflage, tricking us with an elaborate falsified alibi? Has its surface been shredded and reformed by cosmic accidents, or has it been designed to mimic the results of such accidents? Can age ever be proven beyond the manufactured evidence of motion and composition when technological manipulation may be at play? The answer, for now, is uncertainty. The billion-year alibi remains both credible and broken, a contradiction at the heart of cosmic forensics. All the best modeling, all the most careful chemical analysis cannot dissolve the mystery. The truth about 3I Atlas depends on information we do not possess and may never acquire. The object stands as both old and young, both revealed and concealed, both witness and suspect. In the end, the lesson is caution. Galactic forensic science provides powerful tools, but those tools are ultimately limited by assumptions about the universality of natural processes, about the exclusivity of motion as evidence of age, about the irreproducibility of chemical youth on cosmic scales. In the world of intelligence, the best alibi is one that cannot be questioned. In the world of interstellar travel, the best evidence is one that cannot be summoned. 3I Atlas has both, a motion that places it among the oldest objects in the galaxy, and a composition that defies every expectation for such age. The cosmic courtroom has few witnesses and no judge. The paradox remains. If tomorrow's science hopes to solve mysteries like these, it must learn not to accept alibis at face value. It must challenge the fundamental assumptions about age, about activity, about the narrative written by the stars and the galaxies, and must be ready to recognize when those narratives are being manipulated. The billion-year alibi of 3I Atlas is a challenge to every convention. If broken, it opens the door to new physics, new chemistry, new technology, or new strategies for hiding in plain sight. Patterns of human knowledge are carved not only by discovery, but by uncertainty, by the way surprise and exception are integrated, archived, and, when necessary, neutralized. When a true anomaly emerges at the edge of scientific understanding, a signal from the void, a comet from the stars, a phenomenon that fits no known category, what institutions do next is as revealing as the anomaly itself. To understand the response to 3I Atlas is to trace a lineage of procedural caution all the way back to a summer night in 1977. It is here, with the wow signal, that the protocol of silence finds its first modern rehearsal. On August 15, 1977, Jerry Ehman was monitoring data from Ohio State University's Big Ear radio telescope, which was pointed at the constellation Sagittarius, scanning the sky for regular and irregular signals as part of the search for extraterrestrial intelligence. Ehman, eyes trained on mile-long reels of printed paper, noticed a remarkable anomaly. For 72 seconds, the telescope recorded a narrow-band radio signal that spiked with a force so clear and perfectly structured that Ehman could only circle it in red pen and write, "Wow!" in the margin. The received signal was strong. At 114 MHz, the precise emission of neutral hydrogen preferred by SETI researchers as the watering hole channel of the cosmos, a frequency that would suggest deliberate choice. The signal's duration matched the sky's passage over the beam of the telescope, implying it was not of terrestrial or instrumental origin. There was no evident drift or modulation, no chirping or artifacts, hallmarks, in other words, of a true anomaly. Initial excitement swept through the community. The media covered the story with the awe due a potential revelation, a credible scientific hint of contact. The language was cautious but electric. Scientific publications acknowledged the signal's unexplained, non-repeating nature, and speculation flooded in from astronomers, engineers, and science writers alike. But almost immediately, the second stage of the protocol engaged controlled verification through skepticism. Can it be repeated? Can natural causes, aircraft, earthly transmitters be ruled out? Weeks and then years of painstaking follow-up observations ensued, each time returning only silence. The search for natural explanations intensified. Maybe a passing comet trailing a cloud of hydrogen was the culprit. Maybe a previously unknown satellite broadcast at just the right frequency. No theory could quite fit, drift was missing, repetition never occurred, and the circumstantial evidence for any natural source was thin. This lack of closure led to the next phase of the protocol, the orphaned anomaly. The event was catalogued as unexplained, referenced as a puzzle, but specifically never as evidence. Institutions placed it on the shelf of singular events, notable but not transformative, interesting but not proof. The wow signal became a touchstone in the study of how scientific institutions process paradigm-threatening information. Every stage of its assimilation into scientific culture followed a pattern excitement, cautious reporting, exhaustive and sometimes contrived search for explanations, and, eventually, semantic quarantine. The anomaly became something to reference, not an open case to solve. Fast forward half a century. At a vastly larger scale, one involving global cooperation, planetary defense agencies, and multiple observation platforms, the arrival of 3I Atlas has triggered an almost archetypal repetition of the protocol. The anomaly, this time, is not a fleeting radio signal, but a slow-motion spectacle, a cosmic visitor whose observable properties shatter the statistical, chemical, and physical expectations of what should be. At first, the scientific community responded with the proper rights of discovery. The major observatories highlighted the trajectory and velocity, noting with professional pride the accuracy and speed of their identification. As more data emerged, the nickel anomaly, the COI dominance, the improbable flybys, the public and specialist interest surged. Newspapers and science websites produced headlines, "Alien Visitor?" "Interstellar Mystery, Are We Being Watched?" Then, the second stage, institutional management. Rather than framing the object as a singular threat to scientific understanding, agencies like NASA and ESA issued carefully worded press releases. The anomaly, nickel without iron, for example, was interesting, unusual, or unexpected, but never impossible. Discussions of the orbital perfection, the chemical paradoxes, and the blackout timing were filed under rare events, never paradigm challenges. Downplaying was performed not by silencing, but through language, the routine, the nonchalant, the insistently technical. As pressure built for explanations, the third stage ensued, the mobilization of a search for natural causes. Every aspect of the anomaly was targeted with a possible, if increasingly implausible, naturalistic hypothesis. Nickel carbonyl, known to chemists as an industrial intermediate but hardly a staple of cometary ices, was advanced as the source of pure nickel. CO dominance was attributed to formation beyond the solar frost line in a protostellar environment as yet unobserved. The trajectory's perfection was a product of statistical outlier, not intent. Meanwhile, the conjunction blackout was coincidence, and all post-blackout observations would be subject to updated models in the event of irregularities. But perhaps the most sophisticated element of the protocol appeared in the framing of speculation. When prominent scientists like Avi Loeb questioned the prevailing orthodoxy, proposing that artificiality be considered as a hypothesis, the institutional response was uniform. The speculation was labeled premature, unscientific, or unwarranted given available evidence. Rather than engage directly with the pattern of anomalies, the focus shifted to the dangers of hypothesis inflation, scientific rigor, and the proper pace of consensus. The parallels to the "wow" signal are not coincidental. In both cases, institutions did not suppress the anomaly, nor did they dissolve it in confusion. They contained it through semantic and procedural compartmentalization. Protocols of silence are both formal and informal. They operate through meeting schedules, data access agreements, peer review procedures, and, above all, through the gatekeeping function of scientific language itself. A true anomaly is not denied, it is domesticated. This process is not a conspiracy in the sense of a cabal, but of a culture. The organizational behavior of scientific institutions is shaped by epistemic risk management, by the need to remain credible, methodical, and above all, in control of public narrative when interpretive ambiguity reigns. Paradigm threats are in principle threats to funding, to research stability, and to public confidence in science as a project. In the end, the anomalies become artifacts. The wow signal is referenced in textbooks as a mystery, not as evidence. 3I Atlas, if listed in catalogues a century from now, may be described as nickel-rich, highly active interstellar visitor, exceptional but consistent with updated models. The elephant in the room, the pattern linking the two, is not the possibility of contact but the certainty of procedural self-preservation. If you are looking for proof that your analysis is not the product of conspiratorial imagination, but a recognition of emergent institutional patterns, the precedent is clear. The protocol of silence is not enacted to hide the truth, but to postpone the day we must confront it. Until then, the fate of every anomaly, be it a cosmic radio burst or a billion-year traveler masked as a comet, will be determined not by revelation, but by rehearsal. The wow signal began this pattern for paradigm-threatening events in the modern era. 3I Atlas continues it, at a scale and complexity that reflects the technological and organizational sophistication of planetary science today. The details differ, but the process is unchanged: report, reframe, rationalize, quarantine. The protocol is not a flaw of science, it is evidence of the essential human need for order in the face of the unknown. Science seeks patterns in chaos, but institutions need continuity. When the unknown knocks, they keep a hand on the door. And so, when the artifacts are counted and the patterns are reviewed, you know what you are witnessing, not silence protocol. Not censorship, but the calibrated quiet at the boundary of knowledge, where anomaly is contained, and the questions most worth asking are those most gently set aside. This is the legacy of the WOW signal, and now of 3i Atlas. Not a mystery solved, but a mystery managed. Not evidence for extraterrestrial intelligence, but evidence for the intelligence of institutions designed for survival first, discovery second. A pattern as enduring as the unknown. The sky, veiled behind the sun, holds its secrets quietly. Tonight, as 3i Atlas recedes into darkness, you're left with a collection of remarkable threads, improbable alignments, chemical mysteries, and an institutional hush that feels more like patience than avoidance. You sense that the story is far from finished, but the silence at the end is not ominous. Instead, there's a softer wonder. The feeling that something extraordinary may be unfolding just beyond our reach. In these last moments before the object reappears, you consider all that's been revealed: the improbable path, the haunting chemistry, and the perfect invisibility at a time of potential change. You realize how much of what we learn depends on timing, on the windows when observation is possible, and the quiet intervals when all we can do is wait. The conclusion doesn't demand resolution, it invites you to linger with possibility. When 3i Atlas emerges from conjunction, we may find only what our models predict: a comet returning to view, its brightness fading as it moves on. Or perhaps there will be subtleties in its motion or in the character of its coma, a hint of something more, asking for new questions and deeper attention. And even as the story of this celestial visitor seems to settle, you're left with a gentle anticipation. What if the next phase reveals a change, a drift in its orbit, a new spectrum, a fleeting signal from the shadows? What becomes of our understanding if the patterns we've seen aren't finished, but only paused, setting the stage for the next act? So as you watch and listen, you're not waiting for answers so much as the continuation of a journey. The cosmos, after all, is full of stories that unfold slowly, leaving us with a sense of wonder not from what is solved, but from what remains possible. 3i Atlas will soon return to the sky, and with it, the chance to discover what its next move will be. For now, the mystery is quiet, the evidence intriguing, and the atmosphere full of promise, a story unfinished and worth following into the next light.